Hello, welcome everybody to our virtual open night. If you are on Nantucket, you probably already know that it's raining right now. And so unfortunately, we won't be able to have live views with the telescope tonight because of the inclement weather here. However, we have organized this event so that you can see the live views that we would have shown you are kind of interspersed throughout the discussion that we're going to be having tonight. And so what happened was Saoirse Ryan, who's our fantastic telescope assistant, has set up her telescope at her house earlier in the week and has, when we had clear weather, taken the images of the deep sky objects that we're going to be focusing on tonight. So we will be showing you those in addition to some more discussion points. And so just to get started here, first of all, I just want to say, we strongly encourage you to ask questions. Please use the Q&A function, which you can find down in the bottom of your screen. Oh, I don't know why it's, is that somebody just, oh. Is this a Zoom thing for me? Sorry about that. I think I was just having a Zoom problem, but I think I'm still here. So anyways, what I was saying was, please, I encourage you all to use the Q&A function to ask questions throughout the night, and we will try to answer them as they come in. If you've been to one of our open nights before, you know they're very interactive. So we love questions and we love to just respond to your questions. So please do not be shy and put all of your questions in the Q&A and we'll try to take them as they come in. Also, as you can see, there's a note there. If you wish to participate in a drawing activity during this event, please gather some drawing materials now. And we'll explain exactly what that'll be in just a slide or two. Georgia, I think you can go to the next slide. Awesome. So tonight's topic is going to be a tour of winter deep sky objects. As you might know, it's we're around new moon right now, a little bit past. And so there's not much moon right now, brightness from the moon, which means we can actually see, when it's clear, we can see, you know, a very, very dark sky. So we can usually observe these objects in the sky like nebula and galaxies that are inherently not as bright and more difficult to see. And so that was sort of the plan for tonight. Like I said, the weather is not great, but we're still going to be showing you these deep sky objects tonight. And tonight we have Saoirse Ryan, who has kindly provided all of the images that she's taken from her telescope at her house. Georgia Stolle-McAllister, who's the MMO research fellow, who's going to be helping to host tonight's event. And then we have several guest hosts tonight as well, including Natalia Villanueva and Kiana Burton, who are both REU interns from this past summer. Myself, I'm the director of Mariah Mitchell. I didn't even introduce myself earlier. And then we have Gary Walker, who's our telescope engineer, is here as well tonight. And so I'll be helping field questions. And I think you can go to the next slide. Oh yeah, and just one reminder, we are doing these open nights as part of the Nantucket Science Festival, which is happening right now. And you can find out a lot more about the Science Festival. We have a variety of activities that you can do at home. You can find out lots of information if you go to the website that you can see there, mariahmitchell.org, Nantucket Science Festival, and learn about a lot of interesting activities that we have going on this whole week. We normally, of course, do the Science Festival in person, and it's a one-day event here on Nantucket. But given the pandemic, we've transitioned it into a virtual event and made it a week long. And so these open nights are part of that. And I think you can go to the next slide. And at this point, I'm going to turn it over to Georgia.
Yeah, hi. So to start off, I just want to tell you really quickly about the telescope. So even though it's raining, and so we do not have it set up tonight, this is Saoirse's telescope that she's used to take the images that you'll see in a little bit here. And this telescope, it has an eyepiece, so you could just look through it, but it has a camera. And this is how astronomy science is done now, is all with cameras, because with the camera, you can look at an object for longer and collect light on it and get a brighter image and more information and more detail than just with your eyes. But of course, before cameras, people would look through their telescopes and then draw what they saw and look through a telescope and draw what they see to have a record of it. So if you want to participate in our drawing activity today, you can be like those astronomers and sketch the objects that we're going to look at. Or maybe you can use your imagination and see what kinds of like shapes you can find in the objects we're going to look at. Like, are there dragons hiding in there, or eyes or something? Or design your own galaxy. What would your galaxy or nebula look like, and what would be in it? So if you would like to participate and draw, that's great. And then at the end, if we have time, we will give you a chance to share your drawings with us if you want. We can let you show your camera or show your video and show us your drawings, or send them to us over email later. But okay, so that's the drawing activity. And then so we're going to go on to our first object here, which is the Orion Nebula, and I am going to pass it off to Natalia to take over for the Orion Nebula. Oh, and again, everyone, please ask questions.
Thank you, Georgia. So yeah, just to quickly introduce myself, I'm Natalia. I'm an undergraduate student studying astronomy and physics at Harvard. And I'm so happy to be here tonight with all of you. So yeah, starting off with the Orion Nebula, it's also called M42. To get a sense of where this object is in the sky. So what you see a picture of here is the sky, and then the red circle is outlining a star, Rigel. And so the Orion Nebula is within that red circle in that area. And on the next slide, we can see the greater whole Orion constellation, and you can see how there's the 3 stars lined up in Orion's belt. And so I'm sure a lot of you have probably been able to catch Orion in the sky. If not, now you know what it looks like with that belt. It's pretty easy to see. And like the last slide showed, the nebula is right under that belt. All right, so this is a picture that Saoirse took with her telescope. And it's just incredible that with the telescope that you saw a few slides ago, that we're able to take a picture like this and see the different colors of the nebula. So this image is actually 60 individual images that are all stacked together, and each of those images has an exposure of 10 seconds. So that means that the camera was open for 10 seconds to let the light come in and be able to see all of these details. And to quickly just introduce what a nebula is. So a nebula is a dense, cold cloud of gas and dust, and it's like a nursery for stars. It's where stars are born. And so, yeah, we can go to the next slide. So here are some other images of the Orion Nebula. On the left image, you can see the belt, Orion's belt of those 3 stars, and how the nebula is below the belt. And then on the right-hand side, it's like a zoomed in view of the nebula. And so to talk a little bit more about how stars form in nebula, they form out of gravitational instabilities. And these instabilities can happen, for example, if there's radiation or strong stellar wind coming out from a star, and that can kind of push around and blow the gas and dust in different ways, or supernovae from the death of big stars. That explosion can also push around the gas and dust. Or even if there's an object that kind of comes by and the gravity of the object is able to kind of alter how the gas and dust is settling, each of those different processes can cause a gravitational instability or kind of disrupt the gas and dust in the nebula. And that instability will cause certain kind of pockets or sections of the gas and dust in the nebula to collapse. And that collapse is what's going to start forming the core of the star. And that's how the star can form. And so some of the different colors that we see in this image are a result of how the stars are, the luminosity of the stars is interacting with the gas and dust of the nebula. So for example, the red colors that you see, stars that are very hot and young and blue, like the ones you see towards the bottom of that image, those stars radiate powerfully. And so that radiation can excite the gas around it. Specifically, there's a lot of hydrogen gas in these nebula, so it can excite that gas. And that excited gas emits the red color that we see here. And then for the blue colors that we see, they're also due to those hot young blue stars. The blue color is actually light, the radiation that's reflected off of those hot blue stars. And so that's why that's blue. And then another, it's not really a color, but another kind of dimension that we're seeing in the image is these dark regions. And those dark regions are kind of the densest, coldest regions of the nebula. And that's actually where the stars are really forming. Because like I mentioned before, the stars form from that gravitational collapse, right? So it needs, for a star to be born, there needs to be a lot of material, a very dense region of material. And so that's where the stars are forming, in those dark regions that you see kind of towards the left of the image, kind of on the outskirts. And it's dark, even though there are stars forming within those areas, we cannot see their light because there's so much gas that it actually blocks their light. So that's why it appears dark. And so this stellar nursery, the Orion Nebula, is actually the closest object of this type, the closest star forming region to our solar system. And so it's 1,500 light years away from the Earth, and it's about 24 light years across. All right, and in these next few images, these are space-based images taken by the Hubble Space Telescope. What we've been seeing before so far have all been ground-based images, for example, from Sars's telescope, or from other ground-based images. But with these space images, like these Hubble images, we're actually able to use more filters to be able to get a better sense of what different types of radiation there are going on in the nebula. And so this Hubble image is made out of 520 individual images in 5 different filters. And it also has some of those individual images that it's made out of are also some ground-based images, but a lot of the filters that we're able to use, or a lot of the wavelengths that we're able to observe, are because we're taking a lot of the photos from space now. So we're able to see some different colors than we had been seeing before in the previous images. And so the cool thing to point out about these images is that if you look on the left image, you can see there's a very, very bright area right there where the cursor is pointing. And there are 4 stars there, and they form the shape of a trapezoid. So that's called the trapezium, is what that's called. And in the right image, where it's very bright and white in the center, it's a little bit hard to tell, but there's the 4 stars as well. So that's the trapezium of the nebula. And those stars, kind of like the hot blue stars, they're so bright and so hot, and the radiation is so powerful that the radiation is able to kind of blow away and alter how some of the gas and dust is settled in the nebula. So it's pretty cool that those stars are actually able to alter the shape and the form of the nebula. And so this is back to the photo that Sarsha took with her telescope, and you can see the trapezium in the center. Again, it's a little bit hard to tell because it gets a little bit hard to distinguish each of the 4 stars, but they're there. And yeah, obviously they're super bright in that center. And another famous nebula that's in the Orion constellation is the Horsehead Nebula. It's called Horsehead because that dark region looks like a horse's head. And remember, that dark region is where a lot of the stars are being born. And in the next slide, kind of the same like sky view as we saw for the Orion Nebula. You can see that under the kind of edge star in that Orion's belt, there is a Horsehead Nebula. It's encircled in that green dotted line. And you might not be able to tell, but in that red blotchy area, there's a little like patch of darkness. Yeah, the cursor is pointing to it right there. That patch of darkness is actually the horse's head of the nebula. So that's pretty cool that you can see it even with the kind of zoomed out sky view. And yeah, that's all about Orion's nebulas.
Yeah, thanks, Natalia. Orion's cool. It just has so much going on. There's lots of things to find in the Orion constellation. And I'll just say again to everyone, if you have questions, any questions, please write them in the Q&A or the chat, and we would be happy to answer them. I'm going to just tell a really quick story about Messier, because if you remember, the Orion Nebula has another name, which is M42. And the M42 is because it's the 42nd object in Messier's catalog. So there's the M. And Messier was a French astronomer in the 18th century who was really obsessed with comets. He really wanted to find comets, and he spent a lot of time looking for them. Comets are a really big deal at the time because people didn't really know what they were at all, and they like came and went, and so people really wanted to find them. And Maria Mitchell, actually, so who our organization is named after, and who was born on Nantucket, she got her initial fame from finding a comet. So like Messier, she also was kind of on the lookout for comets, but Messier really, really wanted to find comets. And so he spent a lot of time looking at the sky and looking for fuzzy blobs that could be comets. And in the process, he found a lot of fuzzy blobs that were not comets. And they were annoying to him because they weren't comets, and he wrote them all down so that, and like their position on the sky, so that he would know that they were there and they weren't comets, and so that other people would know they were there. And it turns out this list of basically annoyances to him, because they were not what he was looking for, they turned out to be some of the most beautiful and brightest objects that we can see. And they are the targets of lots of study of both professional astronomers and amateur astronomers and astrophotographers, because they're just wonderful. There's star clusters, and there are nebulae, and there are galaxies. People at the time didn't know they were galaxies, but there's lots of them in this catalog. So that's where the M comes from in M42, and other objects that we're going to look at in a little bit here that also are in the Messier catalog. But first, the next thing we're going to look at is not in the Messier catalog, and this is called the double cluster, or also NGC 884 and 869, which I'll get to in a second. But it is in the, if you're in the Northern Hemisphere, it's in the northwest area of the sky. And you can find it if you can look for some constellations around it. So it's in the constellation of Perseus, but Perseus I have a lot of trouble actually finding in the sky. But Cassiopeia is pretty recognizable. It's the one that looks like an M or a W tipped over on its side. Yeah, so this is in the northwest. It's pretty bright. It has a nice distinguishable shape. And if you look at the kind of the center line of the middle of the M, let's say, and you draw an imaginary line between these two stars, and then you point it upwards, you will point to the double cluster. So it's like right up here above Cassiopeia. You can't see it with your naked eye, probably, unless you're somewhere really, really dark and clear. But that's where it is, more or less. So a quick detour, a quick side note here on why is it called NGC, because I think it's a funny story, because this NGC stands for New General Catalog, and astronomers really like acronyms. We have a lot of acronyms for things, but they're not always the most interesting acronyms. So New General Catalog came originally from the, old General Catalog that William and Caroline Herschel put together in the 1700s. And they were very famous British astronomers who published this catalog of nebulae and star clusters. But then they kept finding more and more things, and other people kept finding more and more objects and adding to it. And they published a general catalog, and it had more than 5,000 objects. And then in 1888, this other guy, Emil Johann Ludwig Emil Dreyer, who was a Danish astronomer in Ireland, he combined the Herschel's catalog with some other ones, and he published the new general catalog of nebulae and star clusters. And so I think it's funny that it's the new one and it's from 1888, but we still use it today. It has more than 7,000 objects in it, and NGC is a very like common thing to see like as names for objects. We still use this categorization. The picture in the middle here is one of the original printed pages of this catalog, and it looks like it would be very difficult to use. You have over here the number of the object, and then there's like coordinates of where to find it in the sky and some other bits of information. But it looks tricky to me. Okay, so on to the actual objects themselves. These are, like I said, 2 clusters, hence the double cluster name. And this is the image that Saoirse took with her telescope, and she took it in 2 parts. So for each cluster, kind of separately, with 60 and 74 images for each, and then put them together into one picture. And you can see there's two groups of stars here that are all really close together. And another image. This one is also taken from the ground. This is by an astrophotographer who spent a lot more time, a lot more exposures, probably had maybe had a bigger telescope or different filters to use, and produced this image. But these clusters are called open star clusters. There are 2 types of star clusters. There's open and globular. These ones are open, which means the stars are a bit further apart and from each other, and they're very young. So these are new hot stars that have formed and are grouped together like this in clusters. So just to give you a sort of a scale of age, these stars are on the order of a few million years old, which seems like a lot, but then you compare it to our sun, which is more than 4 billion years old, and these stars are just babies. So these are young, very hot stars. And the 2 clusters are actually very close to each other in real life too. So sometimes you look at the sky and you'll see 2 objects that like look like they're close to each other, but actually one of them is way further away than the other one, and so they're not physically close to each other. But these 2 clusters are physically close to each other. They're separated only by a couple hundred light years, which is small on the scale of space. They probably formed out of the same cloud of gas and material, like what Natalia was talking about earlier in a stellar nursery. These 2 clusters were born at the same time, came from the same material. Yeah. So we'll look at one more picture of these. And again, please send us all of your questions. Any questions are welcome. So this one's an image. The one on the left, the smaller one, is also still from the ground, but then the one on the right is through the Hubble telescope, space telescope, and this image was taken. It's like I think it's called in parallel or parallel imaging or something, where they were actually looking at something else in the field with a different instrument and kind of took this picture in addition on the side. Looks like we have a question. Yay.
We do have a question, actually. The question is, how are you able to tell how old the stars are?
This is a great question. It's hard. Let's see. How do we tell how old the stars are? Sometimes you can tell by what materials they have in them, like what elements are in them, because as stars get older, they're fusing elements together, and so they get more, and you can tell which elements are in them by looking at the spectrum of their light, and different elements emit in different wavelengths. So you can see kind of what they're made up of. I'm sure there are other ways. Regina, I don't know if you want to add things.
Yeah, you might, I think you haven't showed it yet, your color temperature.
Yes, that is next.
From something called the HR diagram, which is basically a plot of temperature and luminosity of the star, and where the star falls in that diagram is associated with the age of the star. The slide that George is showing now has a connection to that. I don't know if you want to talk about this slide now, Georgia.
Sure, yeah. So we'll get back to the age thing in just a second, because that's a good question. But so in general, stars, the color, stars have different colors, and the color comes from their temperature. So the hotter stars are bluer, and the cooler stars are redder. And this is sort of like if you think of a candle flame, or like if you have a gas stove, and the bottom part is blue because that's the hottest part, and the part at the top or around the edges is more red because it's a bit cooler. It's the same idea for stars. So the blue stars are very, 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 very hot. They're also more massive. And so it's a little bit tricky, but the more massive a star, the shorter their lifetime, the less long they will live, because they run through their fuel really fast. Whereas the smaller stars, even though they are less massive, they last longer, which is sometimes hard to think about. But yeah, so like Regina said, stars, you can categorize them on a chart called the Hertzsprung-Russell diagram, or HR diagram, which I unfortunately don't have an image of, but it basically, it has like, it's based on luminosity and temperature. So, and the temperature, which you can also get from the color. And based on that, there are stars that are called main sequence stars, which means they're in their, that's what these are. So these are like normal stars, like they're young or in the middle of their life. They haven't done anything crazy yet. And then once they get older, they change because they're using up fuel. And so the sort of medium-sized stars and smaller stars, as they use up fuel, will puff out into what's called a red dwarf. No, yes, a red giant. Sorry, a red giant, and then the insides will collapse into what's called a white dwarf, and the outside like kind of puffs off into what's a planet called the planetary nebula, which has nothing to do with planets, but just is a cloud of stuff around this middle part. The more massive stars, the really big ones, when they run out of fuel, they collapse on themselves and go supernova. And I think we're going to get to that in just a little bit, because we have a supernova remnant that we're going to look at. So I hope that answered the question about age. It's pretty complicated, but it's based essentially on the temperature. We can tell it based on the temperature and the elements in the stars. Okay, so I think we are on to our next object here, which is the Crab Nebula. And keep asking questions. That was a great question. We would love any more. The Crab Nebula, if we look towards this is in the southwest. Yes, southwest. If you're in the northern hemisphere, kind of around this time right now. And the way to find it, the way that I would look for it, is first to look for the star Sirius, which is very bright. Sirius is also known as the dog star. And I think it's the brightest star that we can see in the northern hemisphere, especially at least in the winter. You can't see it in the summer, you can only see it in the winter, but it's super, super bright, and kind of right now it's like a little bit low in the sky. And then from there, you can look up a little bit and try to find the Betelgeuse, which is part of the Orion constellation. So like Natalia showed earlier, where the Orion constellation is, and the belt stars, Betelgeuse is up above the belt stars, and it's kind of a reddish color. And then if you line up these two stars and kind of keep going up, then you get to where the Crab Nebula is. And this you can't see with your naked eye, but it's there, and you can see it with the telescope. And it's a fuzzy blob, and we love fuzzy blobs. So the Crab Nebula, this is through Sars's telescope again, and it's, I think, 21 exposures, images on top of each other that are each for 30 seconds. So you're letting the camera look at this for 30 seconds at a time and gather all that light and stack them up. And you get this really cool image. You can even kind of see some like structure in it and some slightly different colors. So I think this is it's a really cool image to be able to get with that telescope. And then of course, if you have bigger telescopes and more filters and more time to expose, then you get even brighter, spectacular looking images. So this one was made with a 2.2 meter telescope at the La Silla Observatory, which is in Chile. And it uses lots of different filters and long exposure times, and you get this really bright, shiny object. So just a zoom in view here. The Crab Nebula is a supernova remnant. So like I mentioned a little bit earlier, where when you have a really massive star and it uses up its fuel, so stars are fusing elements together, but eventually they get to elements that they can't fuse anymore because it takes more energy to put them together than it's worth. And and at that point they collapse in on themselves because they don't have that radiation pressure of fusing things that's holding up the star. So gravity pulls all of it in, and the center gets really smushed down to something really crazy dense, but then everything else kind of then explodes outwards, and you get this supernova remnant. The Crab Nebula is especially cool because so there are supernovas going off all the time, all over the place. But this one is really cool because it was observed as a supernova in the year 1054, and it was recorded by Chinese astronomers who, so when a supernova goes off in our galaxy that's close enough and in our galaxy, it looks like a new star in the sky. And sometimes they're even bright enough that you can see them during the day, just because that is so much energy that's coming out of them. So it was recorded as a supernova, or I think they record it as a guest star, in 1054, but this is what's left over. And this material is still expanding outwards, and it's because it's so recent, recent in astronomical terms, astronomers can look at this over several years and actually see this shape getting bigger, which is pretty cool. And at the center of this Crab Nebula, I should mention, this is a nebula, which was also the name of the Orion Nebula, but stars are not forming in this nebula. So this is it has the same name, but it's a totally different object. Nebula is just because nebula means that it's something that looks like a fuzzy blob. So this is a supernova remnant. There are not stars forming here. But it looks like a fuzzy blob, so it's a nebula. And the center of this nebula is a pulsar. So what's left over when really massive stars collapse and go supernova, at the center you can either get a neutron star or a black hole. And a neutron star is really, really, really dense, like unimaginably dense. It's so dense that all of the atoms in it are getting so squished together that even the electrons can't keep each other apart anymore. And so the electrons and protons kind of get smushed together and turn into neutrons, which is why it's called a neutron star. But we can't make anything like this on Earth to, test it out and see how it works, because it's just It's so dense. We can only study it from afar. But neutron stars also emit radio waves out of their poles, and they spin really fast. And some of them spin faster than others, but they turn out to be very good clocks. Like, they're very consistent. You can predict the time. Once you measure the pulses a couple times, you can predict way into the future of exactly when the next pulse will come. So they turn out to be very useful tools for other projects in astronomy, other studies. But these are just to really hammer home how crazy these things are. If you imagine taking something that is almost twice the mass of our sun. Our sun's pretty big, right? Twice the mass of our sun, and you squish it down to the size of a city. Smash it down, then all that mass into such a small area, the size of a city. And then you spin it as fast as a kitchen blender, and you have a pulsar. So these are just incredible. And again, if you were to take a piece of it that were like a teaspoon size piece of it, it would weigh more than Mount Everest all by itself. So these are fun objects, and they're also studied for their own weird properties, but there's one of them at the center of the Crab Nebula. So here's another picture. We're just gonna look at the Crab Nebula again because it's so pretty. And this one is taken in multiple different wavelengths that are added up on top, like stacked on top of each other. So if you look at things in different wavelengths, you get different information out of them, because different elements emit at different wavelengths, and you can see them from different places. So like if you look at the Crab Nebula with a radio telescope, and you just get these radio waves, you see this shape, right? Whereas if you look at it in ultraviolet, you get this much kind of fuzzier looking shape, but they both have important information that you can't get just from looking at one or the other. And the colors are all like added on afterwards. They are, so you look in the radio and you basically get like a black and white picture. And then we're just assigning like everything that we see within the radio wavelength, our image within the radio wavelength, we're gonna say that's red. And we're gonna say that everything within the X-ray wavelengths is purple. And then add them all up so that you get this pretty picture and can see all the different layers of structure and patterns that show up in there. So quick detour to the electromagnetic spectrum because it's so important to astronomy. The electromagnetic spectrum is just light. But light that we see is visible light, which is a teeny tiny part of the whole spectrum. So the whole spectrum goes from everything from gamma rays to radio waves. And like I said, we can only see a little tiny part of it. And we talk about this spectrum in terms of its wavelength. So in terms of the wavelength of the light at different wavelengths. So gamma rays have very, very short wavelengths, and radio waves have very, very long wavelengths, and visible's somewhere in the middle. But since we only get to see this part with our own eyes, it's important that we can look at all the other parts using other tools, like X-ray telescopes like Chandra, or radio telescopes on Earth. Because like I said, you get different information from them. So this maybe gives you a better idea of before what I was saying, where each of these images is in a different wavelength, and then you add them together and get a more complete picture of this object that we want to know as much about as we can, right? All right, we're on to our last object. So I'm going to pass it on to Kiana to talk about Bodes Galaxy, M81. And again, please tell us your questions along the way. All right, Kiana.
Yeah, hello everyone, I'm Kiana, and I interned for the Marai Mitchell Association this past summer, and I study physics and astronomy at Temple University. So yeah, let's get started. The last deep sky object that we're going to be showing you today is Bodes Galaxy, or M81. And as you can see here, this is pretty much to put into context where the galaxy is located and pretty much relative to other objects in the sky. So the red dashed circle indicates where you could find it, right? And then west, we can see objects like Uranus and Mars, and then east, other objects like the Big Dipper here, which is circled in the bigger red circle. Yeah. Okay. Okay, and here is a bigger picture of Bodes Galaxy, which is seen through Sars's telescope. And this picture that you're looking at represents 43 images, right? Stacked images, right? Which were exposed for 15 seconds. So like what Georgia was saying, what that pretty much means is that Sarsha stared at this object for 15 seconds, 43 times, and then combined all of that light so that you could see this image. And Bodes Galaxy is actually a really bright galaxy, right, that we can see from Earth. And so it's not too hard to resolve the structure. You can kind of see some of the spiral arms. Yes, like, yeah. And here down at the left corner, you can see kind of like a scale so that you can see pretty much this. We're looking at a really large field of view. You can skip to the next slide. Yeah, and this is just another image of the same galaxy, just closer up, so you can see some of those spiral arms a bit better. The green effect is just the telescope. And yeah, now I'll describe some more really cool facts about the galaxy on the next slide. So this image is not taken with Sars's telescope. I think that I should probably be a little bit more familiar with the source of this image, but I think that it's a combination of multi-wavelength observations. But just a little bit more about Bodes Galaxy. It was actually discovered by a German astronomer named Johann Bode at the end of the 1700s. And of course, it's named after him, Bodes Galaxy, because he discovered it. But pretty much a galaxy is a collection of all kinds of stars, dust, gas, and most likely other planets, which are all held together by gravity, right? And this one in particular that we're looking at is located about 12 million light years away, right? Which means that it would take, so the light that we see from the telescope, it takes that 12 million years to get here. So every time we stare at this, we're looking at what it looked like actually 12 million years ago. And in terms of how big this thing is, it's about 90,000 light years across. So if you had like a light beam all the way at the edge of the galaxy, it would take that light beam 90,000 years to travel all the way to the other edge. And we call galaxies that look like this spiral galaxies just because of the way that the matter is distributed. So you can see that this distribution creates these cool swirl-like arms, right? And most spiral galaxies, they have this bulge in the center, right, which you can see is the much redder part of the galaxy. And this bulge is a concentration of stars, which are old stars, old red stars, which is where the color comes from. And the outer edges are pretty much just like a flat disk of younger blue stars, which with these spirals or these arms, this kind of arm-like structure in the galaxy. Another cool fact about this galaxy is that it contains a supermassive black hole. So like what Georgia was saying, a black hole happens when you have like a really big star and it's at the end of its life cycle, it dies. And depending on the mass, a bunch of things can happen to it. But in the case of a black hole, what happens is that gravity collapses it. It becomes so dense that it creates this object, right? Where nothing can pretty much escape. It just eats radiation, ambient radiation, or anything that is unlucky to come in its path. And there's a huge one that is about 70 million times the mass of our sun located in the center. For reference, our galaxy, which is called the Milky Way galaxy, also has a supermassive black hole, but this one is about 15 times larger. And yeah, you can skip to the next slide, Georgia. So what's really cool is that this galaxy is right next to M82, which I think is named the Cigar Galaxy, if I'm not wrong. But yeah, you would be kind of looking at it, I think it's like inclined, I pretty much believe, but yeah, it looks weird compared to this one. We can see the structure of this galaxy, or Bodes Galaxy on the left, a lot better than we can see the Cigar Galaxy, but they can be imaged at the same time a lot because they're so close, or close relative to astronomy, because you can see up here, this scale, a really like tiny line represents 10,000 light years, which is big when we think about it, but they're relatively close to us when we're looking at them from Earth. Okay, and yeah, these are images taken with different kinds of light. So on the right, you can see a radio image of Bodes Galaxy, and the M82, or the Cigar Galaxy, is at the top there, and on the left is NGC 3077. I'm not familiar with the more public name that we call it, or the nickname, but yeah, I believe NGC 3077 is also another galaxy. But like Georgia said, again, we look at other wavelengths of light to learn more things about objects. So looking at this galaxy in the radio regime will allow us to see things like the composition of hydrogen, or other elements. And yeah, on the left here, I think that this is taken with normal light, I'm pretty sure. Yeah, and the right is just the radio image. Okay.
Yeah, cool.
Oh, is that?
Thanks.
Oh, that's the
Yeah,
end.
that's the last one. Yeah.
Okay.
I just wanted to add though, because it's also really cool that, like you said, you get more information when you can look at it in two. You're right. The one on the left is optical light, and the one on the right, did I say that right? The left is optical light, the right is radio. But what the radio tells us, which you can't see in the optical, is that all of these three galaxies are sharing gas. So like that hydrogen gas is all mixed up together between the three of them. And that's because they're all interacting with each other. They're all bound to each other gravitationally also, and they're kind of swirling around each other, which is actually what makes the spiral pattern of M81. Because I think it's like every 100 million years or so, M82 and M81 sort of collide, make a pass at each other. And that is what, and then the NGC 3077 also, I think, kind of swirls around and crashes into them as well. And that's what makes those spirals, is actually the interaction between the galaxies. So that's pretty fun. And that when they interact, even when galaxies are crashing through each other, there's so much space even inside a galaxy that mostly the stars don't touch each other. Like it's just the material. Yeah, the material gets all mixed up because of gravity, but not because of like head-on collisions with other matter.
I think what's also really cool is that our galaxy is supposed to, not in our lifetime, but I think it's supposed to collide with the Andromeda galaxy. Andromeda is coming at us really fast, and that's like opposed to the fact that like galaxies are like getting further and further away from each other, right? Since space is expanding. So that should tell you that galaxies move and they have velocity.
Yeah, exactly. And I think because our galaxy is a spiral galaxy also, which means it got its shape from interacting with other galaxies. So yeah, I don't know how many years, it's a long ways away, but yeah, eventually we're going to crash into Andromeda. Yeah. but our sun will die way before that happens. So, and that won't happen for another like 4 billion, 5 billion years. So we're okay.
Yeah.
All right, well, cool. Thank you, Kiana and Natalia. We're at the end here. So first of all, any more questions, and we're happy to answer them always. But also, if you drew something and want to share it with us, we would love to see it. And you can raise your little Zoom hand or write in the chat, and we will make you panelist, which like kicks you out for a second, but then brings you back in, and you can turn on your camera and show us your beautiful drawings or sketches. You can also, even if you don't feel like sharing them today, if you have drawings and you want them to be featured on our social media, you can email them to us, take a picture or scan it or something, and tell us a little bit about yourself. Email it to us at info@mariahmitchell.org. And I don't know if people are raising their hands, so I'll leave that to you, Regina.
I don't see anybody with their hand raised, but while we're giving everybody a minute to work up their courage, you want to discuss this middle? I love the middle picture here. And
yeah, you should tell the story.
Okay, so the middle picture here, you can see it says Lord Rossi's sketch of the Crab Nebula, which is the object we talked about earlier in the night. And, you know, back in the day, people didn't have cameras, either photographic or digital cameras like we have today. And so the way that they did astronomical observations was they looked with their eye and then they drew a sketch. And so this is actually how the Crab Nebula got its name, was based on this sketch that you can see here in the middle that was done by Lord Rossi. And I don't know who exactly looked at it and said that, oh, that looks like a crab, but somebody did, and maybe it was Lord Rossi, I don't know. And that's how the Crab Nebula got its name, actually.
Yeah, I like that story. I don't quite see a crab, but you could use your imagination.
No, it looks a little almost more like a tick if you live here.
The Crab Nebula is maybe a bit more it's not gonna not photogenic. What's like charismatic than the Tick Nebula, maybe.
True. I haven't heard of the Tick Nebula out there yet. Maybe for that reason.
Yeah.
Well, while we're waiting, if anybody still has a question, go ahead and feel free to ask it or share your picture. And while we're waiting, I just want to thank everybody who helped out tonight. Georgia, thank you so much for putting all of this together, and to Kiana and Natalia for coming in and helping out with the presentations tonight. It was really fantastic. And then to Saoirse, of course, for spending time out in the cold on nights that were clear and actually getting those really great images with her telescope from here on Nantucket. And I'll just say again, thank you all for coming. We will be posting the recording of this event. If you'd like to watch it again, or you missed anything, or you want to share it with your friends, we will be posting it on our YouTube channel. And just one more reminder that this is part of the Nantucket Science Festival, which is going on all this week. And there are lots of fun activities, everything free of charge. Everything is done virtually this year because of the pandemic. And you can find out a lot of information if you go to the website listed below at mariahmitchell.org and search for the Science Festival. You can find lots of additional fun things. And I don't see any brave souls wanting to share their artwork.
That's okay. You can always email it to us later if you'd like. And we're glad that you came to watch. Yes.
Definitely. All right. Well, I guess with that, we will say thank you so much for coming, and have a good night, everyone. And thank you to everyone who helped out tonight. If you want to all turn your cameras on and wave goodbye, that would be awesome.
Thank you.
Bye.
Bye, everyone.
Bye. Thank you so much.